Modern geometry discussion. Topic 1 is about breaking boundaries, a journey beyond Euclid's fifth postulate.
So, what do you think about replacing the fifth postulate in Euclidean geometry? It's a bit mind bending, right?
Absolutely. Ignoring the parallel postulate already gave us neutral geometry, but replacing it? That's where things get wild. Hyperbolic geometry is like geometry in a whole new universe.
Exactly, and Euclid himself was cautious about the fifth postulate. It's like he knew it could open up Pandora's box of geometry. Did you get how the instructor said that things get really weird when we replace the postulate?
Oh, yeah, it's like geometry, but in an alternate dimension. I mean, in Euclidean geometry, we have this idea that parallel lines don't intersect. But in hyperbolic geometry, the concept of parallel lines is completely different.
Right, and did you catch the part about working within the disk? I thought it was interesting how anything outside the disk just doesn't exist in this model. It's as if we're dealing with this finite universe with strict boundaries.
Exactly. And what's even cooler is the way we measure distance and angles. Like when we tried measuring the distance in that activity. The distances seemed off visually, but mathematically, they matched. That's so trippy.
I know the whole thing with the segment being bisected even though it didn't look like it was. Hyperbolic geometry really challenges what we think. It's intuitive. It's almost like reality looks different depending on the rules you follow.
That's deep. Imagine if we applied this thinking as a geometry. Different rules, different realities. But honestly, it's tough switching from Euclidean tools to hyperbolic ones. We've been so conditioned to work with perpendicular bisectors, angles, and distances in the Euclidean way.
Definitely, and all the clicking to set the disk center and radius every time, it's a bit tedious. But I get that it's necessary in hyperbolic geometry. Each line segment and angle measurement hinges on that disk center and radius.
It's like each element depends on the disk structure. It makes me wonder if reality is like that too, you know, depending on how we measure it.
That's a next level thought. Maybe that's what math is trying to teach us how to see things from different perspectives.
Topic 2 is about inside the Poincaré disk understanding hyperbolic geometry's unique shapes and angles.
Hey, so this whole semester we've been deep into Euclidean geometry, right? All thanks to Euclid's five postulates. I know they're all important, but I still find it funny how the fifth postulate just causes so much drama.
Right? It's the infamous parallel postulate. Euclid even avoided using it for as long as he could. But when we ignore it, that's how we get neutral geometry. I didn't realize that skipping one postulate could actually redefine the entire geometry structure.
Exactly. And now, instead of just ignoring it, we're adding a twist by replacing it with a different postulate. Like this week, we're learning about hyperbolic geometry. Did you get a chance to try the disk model? It's really cool, but also a bit confusing.
Oh, I know. I opened the file and started with the hyperbolic line segments. It was wild to see that if a line segment goes outside of the disk, it just disappears. It's as if the blue space outside the disk doesn't even exist in this model. Super different from Euclidean geometry.
Yes, and I had to keep reminding myself the disk isn't just the edge, it's the whole space inside it. The tools are all customized for hyperbolic geometry too, which is so different from what we're used to with Euclidean tools.
Like the hyperbolic perpendicular bisector tool, I thought I did something wrong because visually the bisector didn't look like it was cutting the segment in half, but when I measured the distances, they were equal.
I know, that tripped me up too, and since we're still in this hyperbolic world, we can't always trust our Euclidean eyes. The model proves they're equal even though it looks off, and when we measure the angles, perpendiculars actually measure out to 90 degrees, just like Euclidean geometry.
Oh yeah, I had a similar experience with angles. And did you notice how lines in hyperbolic geometry are kind of curved? They look totally different from the straight lines we're used to, yet they still follow the postulate rules of hyperbolic geometry.
Totally, it's interesting to think about how hyperbolic geometry functions with its own unique rules, especially when we're replacing that parallel postulate. Can you imagine if our whole world followed hyperbolic rules? Streets wouldn't be straight, they'd be like these curved, mind bending paths.
Whoa, now that would be a trip. It really makes you appreciate how geometry is just a set of rules we choose to follow. And when we change even one of them, like the parallel postulate, we end up with a total different universe of shapes and lines. Geometry really is all about perspective. Topic 3 is hyperbolic reality, how replacing Euclid's postulate transforms geometry.
Hey, I was going through the video on hyperbolic geometry and there's so much to unpack. Have you seen the part where they show the Poincaré disk?
Yes, the Poincaré disk is fascinating. It's like an alternative world of geometry inside a circle, right? What struck me was how lines in the disk are always perpendicular to the edge of the circle.
Exactly. In this model, lines extend from one side to the disk to the other, and they have to stay perpendicular to the edge. But did you notice that there's also the concept of parallel lines here that's different from Euclidean geometry?
Yeah, that was one of the wildest parts. In Euclidean geometry, you can only have one parallel line through a point outside a line. But in hyperbolic geometry, you get an infinite number of parallel lines through that point. Imagine a point outside a line and drawing countless lines that never intersect the original line.
That blew my mind too. It's like every rule we learned about parallel lines gets a twist. And triangles are also unique. I remember the video showing how the sum of the angles in a triangle is always less than 180 degrees in hyperbolic geometry.
I know, the angle sum is never equal to 180 degrees, and it actually depends on how close the triangle's vertices are to the edge of the disk. The closer the angles get to the edge, the smaller they become.
Right, it's like the edges of the disc compress the angles. And did you catch the part where they try to make a rectangle in hyperbolic geometry? It's impossible to get four right angles in a quadrilateral there.
That was so counterintuitive in Euclidean geometry. Rectangles are everywhere, but in hyperbolic geometry, the fourth angle can't stay at 90 degrees. Even if you get three right angles, the fourth one won't cooperate. It just shows how different the rules are in hyperbolic space.
Definitely, it made me realize how unique hyperbolic geometry is from Euclidean geometry, and the video even mentions that if two triangles are similar, they're also congruent. It's like there's no concept of similar but different sized triangles.
Yeah, that's because distances and scaling work differently in hyperbolic space. It's also new and makes me think about geometry in a completely different way. This video mentioned an app for experimenting with hyperbolic geometry. Maybe we should try it out to see these properties in action.
Great idea. Let's explore both the Poincare disk and the upper half plane model. Seeing these properties visually should make it easier to understand how hyperbolic geometry really works.